I'll go ahead and start. Thank you everybody for signing up and showing up. I mean, it's really supportive just that you guys are all interested in this topic. So thanks also to DVK for last minute helping me with projector stuff. That was making me a bit nervous. But yeah, so one thing that I'm really passionate about is astronomy, as you guys all know about. But to back up before that, for those of you that don't know me, I'm Tinny Washington. I work as a QE in TNP, and I work for Heather Darks. Yay! Yeah. And ever since I was a kid, I would go from home to the public library, and I would get one of two different types of books. Either books about dinosaurs or books about outer space. Those were my two passions as a kid. So ever since then, a lot of my passion for astronomy has been retained, and I still look up a lot of the stuff that's ongoing with that. So before I get knee-deep into the presentation, I want to share with you one of my favorite quotes by Albert Einstein. He said, "Imagination is more important than knowledge." A lot of people, when they study physics, they get caught up in the equations and formulas and numbers and getting that just right. That's not what's as important. For Einstein, what was important was that you be able to simulate and model and imagine what he's trying to teach you and play it out in your mind. That's what's most critical. So for Einstein, before he got into a lot of his research, when he was 16, he tried to imagine for himself what it was like to ride on a beam of light. That's what started his quest for a lot of what I'll be talking about. Speaking of riding on a beam of light, this is a really famous picture in the field of astronomy called a pale blue dot. So what I love about this picture is, well, you'll notice a tiny little dot in the sunbeam on the right.
Right.
That's emanating from Earth. That's emanating from the sunbeam. And that little dot is Earth. This picture was taken about 6 billion kilometers away from Earth in 1990 from Voyager 1. What this kind of shows to me is, well, space is so big, and the stuff we worry about day to day, we might blow it up in our minds. And some of them might be very important and critical. But for me, studying outer space helps prioritize things and puts things in perspective, and helps me realize a lot of things that I blow up in my mind aren't really that important. So the things I'll be talking about today. First, I'll be going into relativity. I'll be using a little bit of math just so that it makes the more interesting stuff that I'll be talking about later more understandable, but relativity will be broken up into two main subtopics: special relativity and general. And once you guys sort of have an intro to those two subtopics, I'll be getting into more interesting phenomena in the universe, like black holes, wormholes, and what happened at the universe's start. So during this presentation, I'm going to try to address three main questions. Is time travel possible? What happens inside of a black hole? And how the universe started. Okay, so this brings me to Galileo. Before Einstein, Galileo had his own theory of relativity, which Einstein built upon. I tried doing a Google image search for Galileo. All of them look like he had an attitude. He looked like he's about to stab the painter, you know. But yeah, this is one of the least grumpy pictures of him. But anyway, so Galileo is known for his theory of heliocentrism, which is the theory that most of the solar system orbits around the sun. Before this time, what was commonly thought of was geocentrism, that much of the universe revolves around the Earth. So he got into a lot of political trouble for this, but that's what you probably guys remember him from school for. But in his theory of relativity, which he developed in the 1600s, he had two main concepts. One is there's no absolute frame of rest. There is no absolute frame of rest. Anytime you're talking about position or velocity, you're always comparing one thing to something else. So when you're saying this car is moving 10 miles per hour, you're not comparing it against some universal standard. You're saying compared to Earth, it's moving 10 miles per hour. And then the other point was the principle of relativity. No matter your frame of reference, if it's moving at a constant uniform velocity, the principles of physics hold consistent with any other frame of reference. So to demonstrate a lot of this, the colors might be off. The sky might be purple. I don't know. I'm partially colorblind, so. But other than that, I think it's pretty amazing. I think the UX team would be proud. Yeah. But yeah. So to make it relatable, I want to talk about a scenario where engineers are shooting each other with Nerf guns, something we see in Pardot culture all the time. You know, kind of like. Okay. So I wanted to use like scooters, but I wanted to like emphasize that in space, it's hard to know who's moving and who's still, because from one person's frame of reference, if someone else is moving at a constant velocity, to them, you might be appear to be moving and they might be still. But anyway, in this example, there's an engineer A on boat A and an engineer B on boat B. From A's perspective, boat B is approaching him at 6 meters per second. From B's perspective, or more importantly, the gun's perspective, the Nerf pellet leaves at 12 meters per second. And I had the number at the bottom down. It's not 24 meters apart. It's 36 meters apart. So let's see how this whole scenario works out from both their frames of reference. The whole event is the dart leaves the Nerf gun and hits engineer A in the face.
Not just hit the
in the face. In the face. Okay, so from engineer A's perspective, boat A is completely still because he or she is on it. Boat B is approaching at 6 meters per second. Now the Nerf speed is not just 12 meters per second, because from engineer A's perspective, it's not only leaving the gun, but it's leaving the gun on a boat that's approaching him at 6 meters per second. So you add this two velocities and you get 18 meters per second. And then the distance the Nerf travels is 36 meters. So the whole time is 2 seconds. Critical to remember the speed and the time. And the distance too. Okay. So from boat B's perspective, boat A is approaching at 6 meters per second, and boat B is completely still. The Nerf speed is leaving at 12 meters per second. The speeds are different from both references. And the distance the Nerf travels isn't 36 meters. It's 36 meters minus the time that the boat moves during that duration, because his target is closing in on him from his perspective. But the time still works out. It's 2 seconds. So this leads me to special relativity. This is a dapper-looking picture of Einstein around 1905. Before he became like a full-fledged research scientist, he was an office clerk at a patent office, and it was actually good for him because he got exposed to a lot of scientific knowledge doing this work. But he built upon Galileo's theory of relativity, and he agreed with the principle of relativity. There was one little caveat. No matter the frame of reference that you're moving in, the speed of light in a vacuum is always a constant. This is kind of bizarre. Remember the previous scenario, the Nerf gun? The Nerf pellet, it changes speed based on which frame of reference you're in. So this was confirmed in an experiment almost half a century back before him in 1851. where they measured light traveling through various mediums, some at different frames of references, and they always confirmed, no matter what frame of reference you're in, speed of light is a constant. So this, if you put these two together, it leads to some pretty bizarre behavior. So let me replay this scenario. Now these two engineers are really tired from, fighting all day with Nerf guns, and now it's nighttime, and they just want to look for each other. They can't find each other. So engineer B is like looking around for engineer A, and he shines it in the right direction and shines it at him. So to make the math more comprehensible, I'm slowing down the speed of light in this magical universe from 300 million meters per second down to 12 meters per second.
Got it.
So in this event, the shining of the flashlight is not important. What's important is the speed that boat B is going towards boat A relative to the speed of light. So it's still, remember in the previous example, it still closes in at about, the boat during the whole event still closes in at about 12 meters. So the same thing is going on here. So let's go through the numbers. No matter the speed, no matter the frame of reference, the speed of light is always a constant. So they're both seeing light moving away from them or towards them at 12 meters per second. The distance that the light travels from frame of reference A is 36 meters. The distance that light travels from frame of reference B is 24 meters. You guys know the basic formula for speed. Speed is distance over time. So if I'm holding speed the same, and I'm holding the distance the same from the previous scenario, something else has to change, and that's time. So time leaving and hitting from the Nerf gun to the engineer's face is 3 seconds, always with the face, I don't know why. From frame of reference A is 3 seconds, and frame of reference B is 2 seconds. So when engineer A looks at his clock, it's moving normally. And then he looks at engineer B's clock, and it looks like it's dilated by about 33% slower. So there's some holes in this example. I'm not actually using the actual equations for time dilation. There's something called the Lorentz transform. I'm just using the basic speed is equal to distance over time formula to make it more comprehensible. Now, remember, I told you about the principle of relativity. No matter what frame of reference you're in, you don't know who's moving, and the principles of physics hold up in both scenarios. This is what's bizarre. A will look at B's clock and see it dilate slower, and you would think that B would look at A's clock and see it go faster, but actually B would look at A's clock and also notice it slowing down. They both see each other's clock slowing down compared to their own. So space-time is dilated symmetrically in special relativity. Okay, that is special relativity, and now I'll be getting into general relativity. So for about 10 years, from 1905 to about 1915, Einstein is still iterating on his theories. And he's thinking to himself, like, what if you include stuff like acceleration? How does that change things? What about gravity? So this is how it's different from the case of special relativity. In uniform velocity, both frames of reference will see each other's time slows down, but when one accelerates away, space-time is dilated asymmetrically. So a classic example of this is the twin paradox. The twin paradox actually can be solved using special relativity, but it's much easier to explain it with general relativity. you have two twins. One is on Earth, and one is on a rocket ship that accelerates far away and eventually returns. When the twin on the rocket ship returns and is back on Earth, he sees that his twin brother is much, much older now. It's because acceleration dilates you slower. So from Earth's perspective, the time on the rocket ship is significantly slower. But from the rocket ship's perspective, time is normal, and he sees everything on Earth speed up. So then what about gravity? Einstein was using his imagination again. So he thought to himself, if you're locked off in a room and the windows are blocked off and you can't see sunlight and you can't see the outside, assuming you're not kidnapped or something, you actually don't know one of two scenarios. You could be on Earth because you feel Earth's gravity pull you down at 9.81 meters per second squared. So you feel that force, anytime you want to get up or something. But let's say you're in a rocket ship and it's out in outer space and it's going away. Let's say you're on the floor of the rocket and the ceiling is in the direction of the trajectory. If the rocket ship is going at 9.81 meters per second square, it simulates Earth-like gravity. You're going to be falling towards the ground of the rocket, and you don't know differences between the two scenarios. In both cases, it's actually force acting on objects. Earth pulling on something versus rockets pushing against someone. Both scenarios are the same. So what Einstein generalized was that just like acceleration curves space-time asymmetrically, so does gravity. So is this all BS?
The secret to eternal life is to just get on a rocket.
That's what I was gonna say.
But from your frame of reference, you would still feel like you're passing normally, and then a lot of your loved ones and network and stuff like that is gone.
That's sad.
Yeah. Yeah.
So if your credit history only lasts 7 years, you get in a rocket.
This is already like
Yeah. So, is there experimental evidence for all of this? So there was a famous experiment in 1971. This was actually surprisingly a low-budget experiment. I think they spent approximately $7,000 on the whole experiment, and a lot of it was using material that they already had with the government, and most of the money was used for getting the air flight tickets. But anyway, they had an atomic clock at ground, and then they sent off from that location 2 airplanes going in opposite directions around the planet. One going due east all the way around the planet, one due west all the way around the planet. So one was accelerated a little bit because of Earth's rotation, and the other was fighting against it. So their accelerations were a little different. When they finally landed back at the original location, they found out when they read the atomic clock readings, all the time dilations fit Einstein's general relativity equations. So that was a huge boost for Einstein's street cred. And in the next picture, you see the Russian cosmonaut Sergei Krikalev. He spent over 800 days in the International Space Station orbiting the Earth, going close to 5 miles per second. It's pretty fast. So in the example I gave, I slowed down time significantly, down to 12 meters per second. But I slowed down the speed of light to 12 meters per second, but it's moving closer to 300 million meters per second. And most human activity doesn't come anywhere close to that speed. So him being in acceleration around Earth's orbit for that long, he dilated an astounding 20 milliseconds. Even our GPS would be off without Einstein's equations. We have to take it into account. If we don't take it into account, our GPS readings would be off by 10 kilometers every day. So that'd be a lot of trouble, especially for people like me with a bad sense of direction. So this confirms or answers one of the questions. Time travel to the future is possible.
Oh.
Travel 20 milliseconds.
Right. So before I get on to the more interesting phenomena in the universe, I'll be talking about how to read space-time graphs. You guys will see this in a lot of literature. So with the way the math works out, you can't really separate times from space. You got to treat it all together. But it's hard to put all 4 dimensions down on 2-dimensional paper, like length, width, and time. So usually people just deal with one of the space dimensions, like length or something, and they put it on one axis and time on another. So you can see the rocket ship accelerating away from Earth, and that grid kind of describes how space-time would get warped. So Earth, it looks like everything is moving at a normal speed, but when it looks at the rocket ship, it sees that it's slowing down. Like everything takes longer to do, takes more time for it to cross a certain distance, and gravity behaves the same way. More massive objects dilate space-time more than less massive objects, just like acceleration does. So this was another interesting thing that Einstein's general relativity taught us. Another scientist described it this way: space-time tells matter how to move, and matter tells space-time how to curve. What does this mean? Imagine space-time is something like a trampoline. If I put a bowling ball in the center, it dilates it significantly. If I use something like a marble, it doesn't dilate it all that much, but it does move towards the bowling ball. So you guys know, kind of like how a motor works. You have like a bar, you have like a magnetic bar, and then you run electric. You have like an electrical wire that you wire around it. If you rotate the bar, it'll generate electric current. That's how you could hand crank a current. But the same is also true if you run a current through that electric wire. It causes that magnet to turn. In the same way, space-time and gravity sort of influence each other. Everyone tracking so far? I just want to make sure I'm not going too fast. Okay. So now I'll be getting into black holes. So how are black holes formed? Our sun probably will never turn into a black hole because it's too small. But for supermassive stars, what will happen close to its death, in its final burst, in its final last breath, it'll blow off its exterior layer, and now there's not enough heat for the star to stay expanded, so it collapses in on its own gravity.
Do all stars die?
Eventually,
Someday?
yeah, because they all burn out.
Yes.
Yeah,
exactly.
Imagine you have a candle. No candle will last forever.
Yeah.
Right. Exactly. Yeah. Before I get to black holes, let me talk about neutron stars for a second. So we know the sun will warp space-time a little bit. Neutron stars are rare phenomena in our galaxy, but they will dilate it even more. Those are super dense, much, much more dense than our sun. A teaspoon of that matter will weigh tons and tons and tons. So it's going to cause space-time to warp significantly more than the sun, because it's, for that little amount of space, it has so much mass and is causing so much gravity. So when a black hole occurs, it collapses to a point where it's not really stable matter anymore. it collapses into like an energy singularity, which is like infinitesimally small. So according to Einstein's equations, not only is it causing the trampoline to spike down really far, it spikes down towards infinity. So it's intense space-time dilation. So what would happen if someone were to fall into a black hole?
Does it just like crush you?
They
Let's get
implode.
crushed and die.
Basically. Yeah. So it depends on whose frame of reference, right? So it's causing time to dilate like significantly. So if we were on Earth and we would see some poor dude get into a black hole, they would look stuck, like they're still there, like right on the edge of the black hole, because time would be like significantly slower from our reading. But from that person's reading, they'd probably be vaporized by the gravitational tides in like nanoseconds, probably, if not less. And they would, yeah. But let's say,
So because it goes down towards infinity, would they always seem there on the horizon? Like from the perspective of, let's say, us viewing them approaching a black hole, so they would never ever, even if we could live forever, we would never actually see them fall into the black hole. They'd always be there on the.
they wouldn't necessarily be on the edge, but you would never see them, right, you would never see them like get to the center. It'd be like an asymptote in high school algebra. Yeah. So,
You can't see past the event horizon.
right.
Yeah.
Right, that's a good point. So this is assuming that you can see past the event horizon. So the event horizon is like this disk around, actually like a sphere around a black hole where light can't even escape, because that's how intense the gravitational distortion is. So just like I was telling you about, like space-time bends around the speed of light. If light is getting sucked back in, imagine how much of a whirlpool it's going to be causing for space and time in there.
Is it sucked back in at the speed of light? It's constant?
No matter what frame of reference you're looking at, light will always be moving at the speed of light
In a vacuum.
in a vacuum.
They're going to move like 5 miles an hour and the chunk comes up weird.
Yeah. Yeah. So Dan brings up a good point. Remember the experiment that I was talking about in 1851? So they weren't actually measuring speed of light in a vacuum, because that's way too fast for instruments at that time. So they were still confirming that light speed is consistent across various frames of reference, but they were moving it through water, which slows it down significantly. Yes. The
Is it
more
older too, if it's smaller?
um,
Like, is a new black hole really big and then it gets smaller?
yeah, so the more massive a black hole, probably the older it is, because it's like taking in matter and just like turning it into X-rays. And
So NASA doesn't necessarily correlate to XYZ space. So it's maybe supermass, but it's not super big from a,
Right.
like a spatial sense in the room. It's still like a pinpoint.
right, the singularity has no volume. It's infinitesimal.
Wish my kids were in it.
Yeah. Yeah. The singularity is infinitesimal, but the diameter around it for where light can escape, that increases in size based on the mass.
So I've heard with like the supermassive black holes, like the ones that center of galaxies, they're because like the tidal forces are so gradual, you can actually cross the event horizon alive before you die, like speed of light.
Oh wow.
That's what Anne Hathaway did, right?
Yeah.
Right.
What? Sounds right.
It doesn't matter to me.
Right. Ooh, mild plot spoilers. You guys remember in Interstellar when a couple of two of the astronauts, they go onto like the huge planet with a bunch of gravity,
I haven't seen it yet, but.
and one of the astronauts remains on the spaceship. When they go back, their friend is like significantly older who stayed on the spaceship. That kind of goes back to that previous slide with how gravity also warps space-time. So I forgot to bring that up. So good point.
Yeah, they thought they were on the planet for like 2 hours,
Right.
and he was on there for like 40 years or something. Like
Right. The dilation was kind of off. Like, it should have like squashed them. But yeah.
Movies aren't always
Yeah. So yeah, to Phoebe, to go back to your question, it's the more massive it is, it only controls like how big like the radius of the event horizon is. Okay. So, do we have evidence of black holes? We can't observe them directly because light doesn't escape them. All the scenarios where I talked about like an astronaut falling in is hypothetical, like assuming you could see that. But we do know they exist because they cause changes to orbits of matter that orbit around it. So we can infer it based on the activities of other bodies of matter. Wormholes, we have no evidence of. Black holes were initially hypothetical, and then we found evidence for it, but wormholes right now are completely hypothetical. So imagine you had a space-time warp where it was like a sheet of paper that was bent. Or imagine that you had to go from like New York to Tokyo. You would think like the fastest way to get to your destination is going around in that curve, but you could like cut a hole right through, like through the center of the Earth or through space-time, and you would get there even faster. So, assuming you could connect like two black holes together, you would have a wormhole, and that would allow much quicker traversals of space and time rather than just going around the long way around the curve. Does that make sense?
It kind of seems like a way to like punk people, like, well, don't go near a black hole, except there might be a wormhole.
Yeah. Yeah.
You have to find out.
Yeah. And even if you did go through a wormhole, it'd come out as X-rays on the other side.
Oh,
So,
sorry.
yeah.
What's I gotta find?
Right. Okay. This brings me to my last point, the Big Bang Theory. So, Einstein, he wasn't always alone in his work. He was working constantly with other scientists and like iterating on his theories even well after he released his paper on general relativity in 1915. So, one of the main author for the Big Bang was a Belgian Catholic priest named Georges Lemaitre. I think that's how you pronounce it. And he was a Catholic priest and an astrophysicist, and he incremented on Einstein's general theory of relativity. He said, okay, we know that the universe is expanding, and not only is space-time like expanding, like everything that we know, it's expanding at a faster and faster rate. It's accelerating. But if we reverse all those equations, it points to a time when all of space-time, all of matter and energy came from like a single point. So this is really, really bizarre. There was actually a lot of pushback against this because before this, scientists assumed that the universe was always in a steady state, and there was evidence that the universe was expanding, but they just thought that matter was coming up out of nowhere and like galaxies were just forming out of the void. So there was a lot of pushback against this because it almost seemed mythological that the universe would have a start to it. But there's a lot of evidence for this. There's redshift and background radiation that's evenly spread throughout the universe. So what came before? So this starts getting into cosmology and philosophy. We don't know what comes before this. And that's why I put before it in double quotes, because time ceases to exist. And we don't know what, like matter and energy to function, it needs space and time. So we don't even know what that means to be before time. But it leads to some interesting points. What came before? Was it, maybe it's some sort of like sentient force behind nature, like the world religions talk about, or maybe it's something much more exotic than the space-time that we're aware of. What kind of matter and energy would have caused something like this? We have no idea. But for me personally, I think as a society to like progress and like figure out where we're going, answering some of these questions will help. That's the last one. So, in conclusion, Einstein, he broke a lot of paradigms about time. Before then, it was thought that time was a universal constant. It's flowing evenly in all places. Time travel to the future is proven. Time travel to the past is completely theoretical. A person who falls inside of a black hole is pretty much effed. Understanding the past, I think, helps us with guiding us in knowing where to go in the future. Hopefully, I've expanded your minds about like how the universe works and made you more curious about it. And I'm super grateful that all of you guys showed up. Oh yeah. Quick acknowledgement. Like Jennifer has been super encouraging in helping organize a lot of this. Like a bunch of my family and friends helped me with dry runs for the presentation. I had to like cut out a whole bunch of material because I can ramble forever. and Jesse and Joe, these are awesome guys in the sales team. They took times out of their sales calls to like help me make sure that the presentation was, relatable and engaging. So thanks to you guys.
Questions? Anyone?
Awesome.
We have time.